Hello, I'm Vinsar Patiraj. We present our work titled Multiclass Confidence and Localization Calibration for Object Detection, which is a train-time calibration technique for object detection. This work was conducted at Mohamed bin Zayed University of Artificial Intelligence with Malitha Gunawardhana and Dr. Mohamed Khan. Despite the remarkable performance of deep neural networks, the trained models with task-specific losses are poorly calibrated. For a calibrated model, even if the model predicts a wrong class, the predicted class should have a lower confidence while significantly increasing the confidence of the correct class, as shown in the top diagram. Currently, the calibration efforts are limited to image classification tasks and mostly focuses on in-domain scenarios. Surprisingly, the research on calibrating object detectors is very limited, although it has several applications in vision-based security and safety-critical systems like healthcare and autonomous driving. In this presentation, we will walk you through our motivation for our work, proposed time-time calibration methodology for calibrating modern object detectors, and the results. We start by showing that the object detectors are poorly miscalibrated for both in-domain and out-of-domain predictions. For these experiments, we use FCOS, a fully convolution-based object detector. Next, we observe that image classification-based calibration techniques are suboptimal for object detection, since it only utilizes the confidence vector but not the localization component of the detectors. The two popular paradigms for calibrating the DNNs are post hoc and train time calibrating method. In post hoc methods, we optimize a single or few parameters on a holdout validation set to rescale the output of a trained model. In the train time method, all model parameters are engaged, and current train time methods typically feature an auxiliary loss function. Train time methods doesn't require a separate holdout validation. In our work, we explore relatively unexplored area of calibration of object detectors, and we propose new train-time calibration method called MCCL, which in its core has an auxiliary loss term. MCCL calibrates multi-class confidences and bounding box localization for the detection task. It is differentiable and operates on mini-batches. We report with extensive experiments on multiple in-domain and out-of-domain scenarios for both CNN-based and data-based detectors. Our method leverages Monte Carlo dropout to estimate four quantities: mean logits-based class-wise confidence, class-wise certainty, mean bounding box parameters, and certainty in bounding box localization. The proposed auxiliary term has two components to calibrate confidence and localization separately. The first component calibrates multiclass confidence by first creating a fused vector of multiclass confidences and certainty. And then for each class, it attempts to minimize the absolute difference between the average fused vector and average occurrences over the mini-batch. In the localization component, we aim to minimize the absolute value difference between the bounding box overlap with the ground truth and the certainty in the bounding box prediction. The auxiliary loss component of the MCCL is the sum of the confidence calibration component and the localization calibration component. Beta is a hyperparameter that controls the impact of the localization component. In our MCCL, we also input the mean logits-based class-wise confidence and mean bounding box parameters to task-specific loss of the detector. We report the calibration error using detection expected calibration error, which is known as DECE, and the detection performance with AP values. We report results for 5 in-domain datasets, including both single and multi-class object detection, including SIM10K, KT, Cityscapes, COCO, and VOC. Our method is able to achieve better calibration performance than the baseline in all cases, including large-scale COCO dataset. For out-of-domain scenarios, we consider 8 scenarios, including CS to CS foggy, and VOC to clip art, watercolor, and comic, and corrupted COCO. Corrupted COCO is a corrupted version of MS COCO, which is constructed by applying random corruptions. MCCL is able to reduce DECE while preserving or sometimes even improving the AP values. A perfectly calibrated model should reveal no gap between the confidence and accuracy. Our method is capable of overcoming overconfidence as shown in confidence histograms and reliability diagrams, and underconfidence as demonstrated in reliability diagrams. The figures reveal that miscalibration error relies highly on the relative object location and/or its relative width and height. Moreover, it tends to increase as we approach image boundaries. Top figure shows the precision, confidence, and DECE over individual parameters Cx and Cy. Bottom figure plots 2D calibration heat maps over object location, width, and height, where each location in a heat map represents DECE. Both figures show that compared to baseline, besides other locations, our MCCL is capable of decreasing DECE at image boundaries. The top row figure shows that compared to baseline, our MCCL allows the adaptation of confidence score at all image locations differently by adjusting the shape of confidence curve accordingly. In conclusion, we study an unexplored problem of calibrating object detector and a proposed train time method, MCCL, for calibrating multi-class confidence and bounding box localization. Our method shows encouraging results in multiple in-domain and out-of-domain scenarios across two object detection paradigms. Thank you for listening.